Go.
Hello, my dear students, and welcome to our first video help session for the problems I've assigned for Chapter 4. And in the first part, we learned about a new reaction type. You know, in the last chapter, they rather dogmatically said there are three reaction types: addition, degradation or breakdown, addition or synthesis reaction, and I forget the third one. Oxidation reduction reaction. I mean, there's so many others. I just made a point. There's a lot more than three types of reactions, and this is one very important one in chemistry. The one chemists do when you see chemists. What are they doing? Mixing solutions together, pouring things together, and something happens. But if you just take blue water and, well, let's say green water and yellow water, and you put them together, you make blue water. But if you take clear water and clear water, you make clear water. If you take blue water and clear water, you make lighter blue water. So you don't often get, excuse me for my hoarseness, I meant to have my coffee cup handy, and I need to move something so I can move my feet. If you'll excuse me, I have my kids' lunchbox supplies here. Now, the new reaction is called a metathesis reaction, although I learned it, and you should know it as what most people call it, a double displacement or a double replacement reaction. And, excuse my harumphing, I like to describe it as changing dance partners, because all you do is separate the salts and switch them around and have them change partners. And this is best described, and for our purposes done, in aqueous solutions. We're going to talk about solutions for these four assignments. But right now, we're going to talk about that double replacement metathesis reaction. And your question is either predict whether mixing each pair of solutions will result in the formation of a precipitate. Now, a precipitate is an insoluble salt that forms, that falls out of solution. It is not soluble in water. And I will talk about solubility charts perhaps later. I use them, or the solubility rules, to go through this. And our first one was iron chloride, aqueous, in water, plus sodium sulfide. And it said, predict whether mixing will result in a formation. Formation of a precipitate. So what I want to do is have the iron go with the sulfur and have them change places, and of course have the sodium go with the chloride. Does everybody know sodium chloride soluble in water? You can dissolve salt in water. It is a soluble salt. So that new substance, excuse me while I grab my pen. It fell out of my pen cap. That sodium chloride is soluble, but this new compound, FeS, iron sulfide, is insoluble. How do you tell? Well, this wasn't a very good one because I'm not sure I gave the rules for sulfides in the list of rules. But my main rules were, look, if it is a nitrate or acetate salt, it's soluble. Just about everything else is insoluble, except when we look at the other rules. The other rules are, if you're a group 1 metal, lithium, sodium, potassium, cesium, I'm trying to remember them all. I have my periodic table up so I can tell you. Hydrogen, well, we won't consider it a group 1 metal, but lithium, sodium, potassium, rubidium, cesium, and I have my reading glass on. It's too far away. Cesium and francium. and we don't encounter a lot of rubidium and francium and maybe only rarely cesium. So we're talking lithium, sodium, and potassium. Those salts of those metals are always soluble. And so sodium chloride is going to be soluble, as is sodium sulfide. Iron is not a group 1 metal, it's a transition metal, and it is in family 8, but it is insoluble. It forms an insoluble precipitate. Okay, so this forms a precipitate. For the second one, it's sodium hydroxide plus phosphoric acid. This is an acid neutralization reaction, which we're going to talk about in the next assignment, and that we talked about in the second one. But this is still, if I have sodium phosphate, PO4, let me just write it properly, sodium phosphate. This would need 3 of those because phosphate's always -3, sodium's always +1. You can actually buy this in the store as TSP, trisodium phosphate. This is soluble because it's a group 1 metal. And the next one would be the hydrogen goes with the OH minus. Well, what do you get when you mix hydrogen and hydroxide? Not Ho, but H2O, water. Okay, so this one is no visible reaction. In the laboratory and in chemistry, 3 things tell me a reaction has occurred. Formation of a precipitate. That's what we're concerned about in this assignment. But also evolution of a gas bubbles, and a change in color. Those are situations in a test tube, in an aqueous solution, where you can visibly tell that a reaction has occurred. What we're looking for in this assignment are precipitates. The third one mixes zinc chloride with ammonium sulfide. So I'm going to make 2 compounds. Ammonium chloride. This NH4 stays together, NH4 plus and Cl minus, ammonium chloride. All ammonium salts are soluble. And zinc sulfide, another sulfide. This is an insoluble precipitate. So, for question number 3, when it says, which, will mixing this pair result in formation of precipitate? Yes. And if so, the precipitate should be identified. So this is what you need to say. For number 1, iron sulfide. For number 2, you need to say no visible reaction. And for number 3, you need to say zinc sulfide. So let me do the other 3 before I go on to the next page. If I substitute and change dance partners in this reaction where I have phosphoric acid again and potassium hydroxide, I will mix this potassium with this phosphate, and I will make potassium phosphate, which is soluble. It's a group 1 metal. According to the rules of solubility, it's soluble. And I will mix this OH with this H. It's not balanced. I would need 3 of these, but I will make hydrogen plus from the phosphoric acid and hydroxide from the potassium hydroxide, and I'll make water. So again, number 4 is no visible reaction, what we call NVR. Sorry, my paper's moving on me as I write. That's a V. NVR. Next one, potassium carbonate, aqueous solution, is mixed with an aqueous solution of barium chloride, and I'm going to get potassium chloride, KCl, going to get 2 of them, and barium carbonate. Potassium chloride's a group. Potassium is a group 1 metal. Its salts are all soluble. Barium carbonate is a carbonate, and this barium, this group 2 alkali earth metal, forms an insoluble salt with the carbonate anion, and this one forms a precipitate. When I mix these two solutions together, barium and carbonate will come together, potassium and the chlorine, and then the barium and the carbonate, there it is, will come together to form the insoluble barium carbonate precipitate. And this last one, barium nitrate, all nitrate salts are soluble, and sodium sulfate, all group 1 metal salts are soluble, come together, and I'm going to form sodium nitrate. Not worried about balancing it. I'm just doing my dance, changing my dance partners. Nitrate salts are soluble. Nitrate and acetate salts are soluble. That's the rule I want to remember. Okay? Sodium group 1 metal salts are soluble. Just always watch out for those, what I call the terrible three. Silver, mercury, and lead. They frequently form insoluble salts. Unless it's, if I buy a silver salt or a lead salt, it's almost always lead acetate or lead nitrate. Finally, in this one, I have barium sulfate and this forms an insoluble precipitate. Okay? Excuse me while I quiet down my puppy. Sorry, he was chewing a bag. Now, the next one says, if I may get to it, I don't have page 2, but let me pull it out here. That's 1 through 6. It says, pick one of these reactions that results in formation of a precipitate. So that means not reaction 2 and not reaction 4. Pick one. I'm not going to do them all. You can do one of the ones I do, or you can do a different one. If you pick a different one, I'll give you extra credit. But I'm going to do 2. I'll just do the first one and the last one, since I've already written them down. So, the first one, it says, write 3 things. A balanced chemical equation, a complete ionic equation, and a net ionic equation. So I'm going to do all 3 things for each of these. I'm going to start off in green and do the balanced chemical equation. Okay? Iron chloride, aqueous, plus sodium sulfate, aqueous. I'm not sure I want to use that because it's not writing well. React to give me iron sulfide, and this is going to form a solid, a precipitate that falls out. That was our answer for the question on the first page, plus NaCl. But I need to balance it. So I have 2 sodiums and 2 chlorines. I'm going to form 2 of those. So there's my balanced chemical reaction. This is iron 2 chloride plus sodium sulfide forms iron sulfide plus sodium chloride, common table salt. But notice there's 2 sodiums here and 2 chlorines here, so I need a 2 there, and everything else is balanced. That's my balanced chemical reaction, okay? And now, this iron chloride, let me do the net ionic equation in another color. In solution, it becomes iron 2 plus ions plus 2 chloride ions. And this sodium sulfite becomes 2 sodium ions plus, that's aqueous, 2 sulfide, 2 minus ions, AQ. So, this iron chloride, don't write this down, but it splits apart into these 2 ions, these 2 species, when it dissolves in the water. The ions separate. It's an electrolyte because now we have charges in the water to propagate an electric current. So a solution of iron chloride will conduct electricity, and this one. And of course, these react to give me the insoluble iron sulfide. Notice I put solid there, plus 2 sodium plus aqueous plus 2, because there's 2 of them, Cl minuses aqueous. That's my complete ionic equation, because this, these 2, when you dissolve them, give you 2 of each type of ion. Complete ionic equations are really not much use except as a tool to get to the net ionic equation. But this would be, for example, what did I number that? Question 8. If I'd chosen this one would be 7. I'll keep it in blue. And of course, I didn't say this, but my sodium sulfide would break apart into 2 sodium ions and 1, I shouldn't have had a 2 there, 2 sodium ions and 1 sulfide. Okay? You don't need how these break apart. But notice I have, like a mathematical equation, 2 sodiums on this side and 2 sodiums on that side. And I have 2 chlorides on this side and 2 chlorides on that side. You don't need to cross those out. But my point is that when I treat this like a mathematical equation and see terms that are present on both sides, I can do away with them. And so my net ionic equation, this is question 9, is Fe2 plus in aqueous solution plus sulfide 2 minus in aqueous solution. These are state functions. These are written as lowercase letters that are also italicized. That's going to give me the solid insoluble iron sulfide precipitate. That's your net ionic equation. Because I took out my spectator ions that aren't actually participating in that reaction. So let me go ahead and do the last one, and just do another one. That might be, well, it's actually not that much more challenging. But here's barium nitrate, and we're going to make barium sulfate, the insoluble solid precipitate, plus change partners, sodium nitrate. But notice I have nitrates minus 1, bariums plus 2. So I have 2 nitrates for every barium, because I need a neutral overall charge. So, and sodium is plus 1, sulfate is minus 2. This is all open book. You can look and see the charges on these polyatomic ions. So I'm going to have 2 sodiums and 2 nitrates. So I'm going to make 2 sodium nitrates. Sodium's plus 1, nitrates minus 1. Dissolving in water, because nitrate salts are soluble and sodium salts are soluble. So let me write my complete ionic equation. Separate everybody into their component ions. So for these compounds, barium nitrate, when I put this in solution, this is equation number 6, but this was number 7, the balanced chemical equation. Okay? If you choose this particular example from the first page to answer 7, 8, and 9. 7 is write the chemical equation, balanced chemical equation, molecular equation. 8 is write the complete ionic equation, and 9 is write the net ionic equation. So now I have a balanced equation. My coefficients are 1, 1, 1, and 2. I don't need to write the ones because it's understood. It's like the difference between saying 1x and x. It's the same thing. If you put the ones in there, that would be fine too. So let me write all these. Barium nitrate breaks down into barium 2 plus 2 nitrate minuses. And all of these are aqueous, in case I forget it later. Plus 2 sodium ions, 2 Na plus 1s, plus 1 sulfate 2 minus. All aqueous. And they react to form the insoluble barium sulfate that precipitates out. I mix these two solutions together and it instantly turns cloudy and precipitate. I wait long enough and you can see it settle down to the bottom and coat the bottom of the test tube or the beaker or the flask. Plus 2 sodium plus aqueous plus 2 nitrates minus aqueous. Same with the charges. If you have a 2 minus, you have to put 2 minus. If you have a 1 minus, you don't need to put the 1. You can just put a minus. Sometimes I even put 1 minus if I'm trying to give something emphasis. Then finally, this one asks for, and you don't have to do this for one. Just pick one of those reactions and practice balancing equations some more. And then come back and write the complete ionic equation. Think about every species present in that aqueous solution. And then get rid of your spectator ions. 2 nitrates over here. 2 nitrates over here. 2 sodiums on this side. 2 sodiums on that side. That leaves me with barium aqueous ions plus sulfate ions aqueous coming together to form the insoluble barium sulfate salt. And that is how it's done. So I will I was planning on posting this on Thursday. I don't think I'm going to make it up there on Thursday. So I'll probably post this video help session for 4.1 on Friday, or you'll know when you see it. And the other thing is I'll probably post 4.2 at the same time. And then I'll post the ones for 4.3 and 4.4 next week on Monday, along with perhaps another piece of work for you. So until then, stay safe and goodbye.